Okay, chemistry time, advanced chemistry, chemistry time, parenthesis, advanced, chemistry 2 time, chemistry 2 time. I'm going to even write that because I think I've done this every time. Chemistry 2 time, good. Yeah, that's lovely. We're talking today about, I'm going to call this thermochemistry. And that is what it is, so it's not just I'm calling it that. That's the truth. Is my mic picking up? Okay, good. We're going to start very simply out, and I'm going to do this only briefly because 1, you've already done it in your lab, and 2, I have videos from last year in this class and from physical science last year and this year of this. But the first thing we're going to talk about just real briefly is Q equals MC delta T. Q, we kind of agreed upon is the abbreviation for heat energy, so Q is heat, M is mass. We had this on the board in the lab, so this is review. C is specific heat, which is a known value for any given substance. And then delta T is change in temperature. We have to measure the change in temperature, and it doesn't really matter whether it's Kelvin or degrees Celsius because specific heat. And this is in joules per kilogram degrees Celsius usually, or kilogram Kelvin. They have to match, so I'll just make this one say degrees Celsius. Mass in kilograms, and then heat we measure in joules. This is a standard plug and chug equation. You should be able to do this. I'm not very worried about it. And I don't want to spend a terribly long time on this lesson in general, and so we're going to have to move on because that's pretty simple. Do you have questions about this before we move on? Or does this make pretty good sense to you since you did it in the lab? Do you understand what each of these quantities mean? We know what heat energy is. You've certainly been exposed to physically, but you've been aware of the idea of heat energy since you were a tiny little kid probably. You know what heat is. You know what mass is. We talked about that several times. Specific heat we define as the amount of energy it takes to change the temperature of an object, of 1 kilogram of that object, by 1 degree Celsius. And then delta T, of course, is change in temperature. Would you be able to manipulate this equation to find any of these things? Usually what we're doing when we do something called calorimetry is we're trying to find the specific heat of a substance. We measure how much energy we put in, we know the mass, and we measure how the temperature changes, and that gives us C.
Why isn't it just C?
Solve
for C.
You solve for C. One reason is that I like to have equations all in one line so that whenever we're manipulating, we can just divide in one step instead of having to put in the numerator first. And another reason is that it works, the units always work out, but if we're trying to find the simple value of heat, that gives us this equation, which is Q. I'm gonna get these out of here. Let's get this one. There. Okay. See ya. Okay. The next thing I want you to write down. This is where it gets good. Is Hess's law. Hess's law. I'm going to quote Hess's law so that I get it right, and 2, so that you have the correct information. Hess's law states that if you can add 2 or more thermochemical equations to produce a final equation for a reaction, then the sum of the enthalpy changes for the individual reactions is the enthalpy change for the final reaction. So in basic terms, if 2 or more equations can be added to get a third, the sum of their change in enthalpy, delta H, can also be added to get the total delta H, where delta H is change in enthalpy. We'll talk about enthalpy in a second. I want you to write that down first. The book's definition of enthalpy the heat content of a system at a constant pressure. So it's not the same as Q, which is the heat energy. It is measured in joules, or usually kilojoules actually, but it's not the same as heat energy because enthalpy is, for one thing, it's at a constant pressure. But for another thing, we always measure it as delta H, and this is very important because it's impossible to know how much enthalpy a system has. It's impossible to know how much heat energy a system contains. You can't ever know the exact amount, but you can measure the change in enthalpy. I'm trying to think of a layman's example. It's like if you had a magical can of soup that no one can ever figure out how much is in this can of soup. It's an infinite can of soup. You never know how much, but you could pour out a cup, and then you know it has a cup less. Do you see what I mean? There's no such thing as a magical can of soup, but it's kind of like that for enthalpy. We can't measure enthalpy, period. But we can measure change in enthalpy. We can measure how much leaves or comes into a system. And so what this means is that we can, the example your book gives is if we have this chemical equation, 2S plus 3O2 yields 2SO3, and we want to find the change in enthalpy. So this is we're trying to solve for this. Trying to find the change in enthalpy of this equation. And we also know that S plus O2 yields SO2, and that change in enthalpy is equal to negative 297 kilojoules. Then we can, what else does it give us here? And then it also has SO3. These are the things that we know. SO3 yields 2SO2 plus O2. And that change in enthalpy is positive 198 kilojoules. So we have these different chemical reactions. You'll be given these, and there's also an appendix in the back of your book, and you can find these online too. How much time do we have left? 9 minutes, like 3 minutes left?
9 minutes.
9 minutes, okay, we can make it work in 9 minutes. There's an index in the back of your book that I want you to look at. Dang, I always mean to remember it, and then I always forget it, and then this is the result of that. Troublingly, it's only one page, too. It's a table of what we call standard enthalpies of formation. And it's on page... You find it? It's in the back somewhere.
What is it? Specific heat?
Yeah, no, it's standard molar enthalpies of formation. It's before the glossary. It's before the properties of elements. Specific heat. Oh, no. Heat of formation values on page 975. You might even bookmark that. But this is the change in enthalpy of formation if these are synthesized from their simplest elements. So for instance, if we look at the one for SO2, do you see SO2 on here? They're alphabetized, which is kind of crazy, but I guess it's the best way to do it. Do you see the one for SO2? What does it say? Yep, and that's what we have here, negative 297. This is rounded. But what it means is that if each of these, when these things are synthesized from their simplest elements, like SO2 from S and O2, that's how much the change in enthalpy is. And so you can use that. There's one for SO3 too. What's the one for SO3 say? Oop. Oh yeah, because what this is a decomposition reaction. So they've given us this. The given is that we know the standard enthalpy of formation for SO2, and we know this other, decomposition reaction of SO3. Because see, these are both different from the one that we have. But what we need to do is, since Hess's law says that if we can add these two reactions to get this reaction, which we can, you can see how they kind of, we like squint our eyes and squish these together, they are this equation. You see, we have SO3 as a product, that we can also add their enthalpies of formation. But the trouble is we can't just straight up add them. You see the problems? Well, for one thing, SO3 in our given is a reactant, and in the one that we're trying to find, it's a product. And for another thing, we have SO2 in both. So what do we need to do? Well, what do you think we have to do if it's on the wrong side? How does that change this value, do you reckon? Okay, so if right now it's a, yeah, it changes it to a negative, exactly right. So let's write that down. If a species, I'll put A instead of the, if a species is in the reactants but needs to be in the products, or vice versa, or I'm going to abbreviate V, that seems good, doesn't it? Or vice versa, just change the sign. Change the sign. Simple as that. And the other thing, that's kind of thing the first. Thing the second, this is not going to show up on the video very well, I'm afraid. Thing the second is, what else do we notice? How is, for instance, how is our sulfur different in our givens than our find? Just the elemental sulfur here. Yeah, how's it different in the given than the find? Yeah, it's only 1 in the given, and there's 2 in the find. So what do you think we need to do then? You successfully answered this one. What might we do with the numeric value of enthalpy of formation if we have to, yeah, we double it. And then we multiply species delta H by the same amount as they are in the equation. So basically, and we should, I'm going to have to erase this top part up here. But basically what we do then is we show standard enthalpy of formation. Okay, now check this out. You see delta H is change in enthalpy. The lowercase f, the lowercase Latin letter f down here, stands for formation. So that means it's the enthalpy, or what we sometimes call the heat of formation. And this little naught in the upper right corner, which is 0, but we call it naught, that means that it's the standard one. That means for 1 mole of this. We could do it for any number of other moles, and then we just multiply the answer. Like if we had 0.0917 or whatever, we would just multiply the answer by that. But this is for 1 mole. Okay, so of SO3, oops, SO2 is negative 297 kilojoules. And we agree we need to do what with that one to get it to be like this equation? Multiply that by 2.
Why'd you make it negative?
Because we're doing this one. It is negative already.
Oh, it is.
And then for the other one, for the change in enthalpy of SO3 yields 2 SO2 plus O2. This is not the standard enthalpy of formation for SO3, but for this one it equals 198. What do we need to do with that one? Make it negative. Okay, I'm going to show that we multiply that by negative 1. And then we just add these together. So negative 297 times 2. Negative 297 times 2, calculator girl, or boy, non-gender specific. Negative 297 times 2 plus negative 198. We'll do more practice with these. So negative 297 times 2, enter, and then plus negative 198. Do you see why the 198 is now negative? What did you get? Are you with me so far, Skylar? Or if not, which I can see you're not, we will do more practice, but what questions do you have? Do you see where I'm getting the numbers at least?
Yeah.
These were given, and then we followed these rules to say how to modify them. And so now Hesss has multiplied this one by 2, multiplied this one by negative 1, and added them together, and you get, you have to add a negative. So it's still negative 297, but times 2. So this we should have negative 594 minus 198. Yep. I already know what it is. You know how I already know what it is? The book. Which, that means we got the right answer. But do you see how we did it? We think about this and these and what needs to be done to these to change them into this. And then we just do that to the numbers too and add them together. It's just this little thing is the kicker. This is Hess's Law, which just says we can add them. That's all. That's really all Hess's Law is. Your book goes on to talk about heat of enthalpy, standard enthalpy of formation, and standard enthalpy of fusion and vaporization. It talks about Gibbs free energy, talks about entropy, and we will talk about all those things as we go over your chapter review. But here, let me give you 2 pieces of advice. Read your book. You have to. Watch the video I did last year on this. I took another video about entropy. I think it was last year. Also, guess what? You don't have to watch that one. There are good YouTube videos that have people who actually know what they're talking about doing it. But this is the main math for our chapter. Dally, that face hurts my feelings. I'm trying my best.
That's not what I'm saying.
I know.
You said you're not even confident in yourself. You're like, watch somebody else. They're
Well,
better
but
than
there are people who are better than me. But listen, this is the main math that we're going to do. So read your book, watch a video, and you have your chapter review due Wednesday. Tomorrow we will be working on this in class, okay?